exponential model for our data, remembering that you have to make a correction on the data. There's one of those data points you can't put in, right? If you try to put this one in, the model will get pissed. It knows it can never get to 0. Aaron, back to your awesome question from before, because of this argument, right here. You can keep this bad boy going all day long, yes? This will never get to 0. This will keep getting smaller and smaller and smaller. It'll never ever zero out. It'll only keep getting smaller and smaller, but it'll never actually reach 0. That's why the TI gets upset. If you're trying to make an exponential model equal 0, it will not let you. So you take that last bit out. If you guys did the exponential quiz from this week, I think there was an exponential quiz up for this week, yeah? You had to do the exact same thing. You had to take out your last data point. I've got more exponential quizzes planned for you guys over the next couple weeks, so you'll have... what you got, Michael?
I got a funky paragraph full of useless information.
You are in a program. Let's get out of there. Okay, now you're good.
Thanks.
When in doubt, hit the second function button and remember directly to its right, and that should get you back to your home screen.
Okay.
Safe and sound.
Thanks for saying that.
Oh, it does? Oh, plot it, yes, but run the regression, maybe not. Yeah, you can plot this. You can plot the 0 point just fine. You just can't run the regression on it. Yeah, you can plot how many points you want, but the mathematics behind the regression calculation get a little pissed. So let's take a look. Not many data points. Ooh. As Kelly said, it should be over quickly. Do we need this? No, don't need this. Now, after you get your model, see if you recognize any of the numbers in it. There we go. And here's the scatter plot. There he is. Hannah, would you mind killing one of those lights? That'd be awesome, thanks. I'm going to change that y-axis. That scaling's annoying. Let's make it like 5. Does it have a similar shape? Aaron, you made a very, very cool statement last class. You said, hey, that card curve looks like the coin curve. Does this one look like both of them? It does, doesn't it? It's got that same kind of, you know, steep, flattening, never touching, but flattening. Yeah, very, very similar. Very, very similar. Let's find the curve. Let's find the curve. So we use stat calc, xreg, exponential regression. Here she comes. Okay. There we go. We got ourselves. Once again, it says 20. Well, actually, that rounds to 22, doesn't it? 21.8 rounds to 22. So it's overestimating how many of us were in the room. But that's okay. We expect that. It shouldn't hit it perfectly. It's best fit line. What's the matter, Kelly? You look happy.
Oh, my shoulder. No, it's my shoulder.
Oh, you showed me too. Went down on the ice. Yeah. So 22. I understand the pain. I totally feel you. So 22 is our base. It should be 20. Yes, it should be 20. But it's a best fit regression. It doesn't know that it's 20. It just knows it's going to fit a curve to those points. So we've got ourselves a model now for this one. Come over here. Y equals 22 times, we'll call that 0.21, huh? How's it fit? Anybody graph it? That's pretty freaking awesome, yeah? Pretty damn good. Pretty damn good. So do those two numbers make sense? The 22 times the 0.21 to the x. I think the 22, we understand. What about the 0.21? What's that all about? 0.21, what's this? Now realize it's not perfect. You guys actually quoted the number that it theoretically should be last time. But somebody just say it. Be brave. You know it.
The rate.
And the rate is what?
The amount of people left.
Exactly. What should it be theoretically? If we're pulling until we get hearts, excuse me, if we're pulling as long as we get hearts, what percentage of hearts is in the deck? 25%, yes, 25%. So that means we should only be leaving behind 25% of people each trial, yes? That's what the 21 is very close to. The X is the number of pulls, just like it was over here. It's the same number of draws. Actually, the X and the Y for this are the same as the X and the Y for this. Y is how many are remaining after X pulls. But the rate is changing. And Kelly, you intuitively had a feel for this right off the bat. You're like, this is going to be over quickly. Because you're only leaving behind 20, well in this case 21, but theoretically 25% of your population each time. Does that make sense? We can drag it out if we want, and say keep pulling until you get an ace. We'd still be doing that from yesterday, wouldn't we? Because there's so many other things besides aces. This sped the process up quite a bit. Very quick exponential decay. Very, very rapid. That's why the curves rocketed out like this. So now what I want to do real quick, just to show you guys, I'm going to put three curves in the calculator at once. I'm going to call them the ideal curves. The ideal curves. You guys can do this if you want, or just check it out if you want. I want to go back to what Aaron said on Monday. So what I'm going to do is I'm going to erase that curve and turn the scatter plot off. I'm going to put in the ideal curve for experiment number 1. 20 people flipping coins until they get heads. It should be 20 times 0.5 to the x. Now good, I like what Kelly's doing. She's looking over there at the actual regression curve, which is 21 times 0.53 to the x. This is the perfect curve if we did it for infinitely many trials. It would average out to this. We didn't do it enough to, we didn't do it enough to get to infinity, obviously. Is that fair, Kel?
Yeah.
So this next one would be 20 times 0.75 to the x power. Very close to what we got. But again, since we only did a fixed number of, I think we did 10 trials, it won't be perfect. And the last one we just did should have been 20 times 0.25 to the x power. Those are your three curves. Now I think I can, let me try something here. I think I can make them all, I know Tom can do it because his TI does color, but mine doesn't. So I'm going to try to make them look different. We'll do spermian. I just lost the crap. I went through spermian. Hang on. There's spermian. Okay. Now what I'm going to do, take a look at this. If you want to do this, we can do it too. But I'm going to graph all three of these things. Okay, here, that is the coin flip curve. I'm going to pause it right there. Okay, there's the coin flip curve. This is y equals 20 times 0.5 to the x. I'm now going to graph y equals 20 times 0.75 to the x. Here he comes. Now watch Spermy. Spermy is 20 times 0.25 to the x. Spermy. And you know what? Spermy sucks. Hang on. Let me make it dotted. Let me make it dotted. Hang on. Let's see if this works better. 0.5, 0.75, and this is there. Yeah, that's a little better. It's kind of sucky anyway. Now, they all have the same shape, don't they? I mean, ish. What are they all doing? What are they all doing, especially if we take our windows out further? What are they all doing as we go to the right? Now we can mess with our window in a second if you want to. I think we should actually.
They're all even out, approaching zero.
They're all approaching zero, aren't they? So that's how they're all similar. Hey, notice how else they're all similar? What else do they all have in common?
Intersection.
You catching this? Every one of the three of them goes through that point right there, which is the point 0, 20. Now that hopefully makes sense. If you plug 0 into any of these equations, the exponential part equals 1. 1 times 20 is 20. So hopefully that makes sense. All of our curves did the exact same thing too. The difference is in how fast they get to 0. How fast they get to 0, right? The 0.75 depreciation, or I should say, it's actually not the 0.75, it's the 0.25 depreciation, it's 0.75 maintenance, takes longer to fall than the 0.5, which takes longer to fall than the 0.25. Clearly, the quicker the rate, the further it's going to go down more quickly. But they're all getting to 0 eventually. The question is, how fast are they getting to 0? This guy's getting there more slowly than this guy, who's getting there more slowly than this guy. So Aaron, that question you asked on Monday, I haven't stopped thinking about it since then. They all do have that in common. Now the trick is, if you mess with your window now, if you start messing with your window, let's go to the right more, let's go past 3 trials. Go past 3 trials. So if you press your window button, right now the TI has it set at X max of 3.3. Go out to like 10. Go out to 10. And see what happens. You just press graph. There's point 5. Here's 0.75. Predict where 0.25 is going to go. So you see what's happening? They're all ending up down here. But even if you go out there and Z-box around that region, you're going to see 3 finite pieces. Let's do it. Let's Z-box. Remember Z-box from last time? Let's go out there and Z-box a little bit. There we go. Okay, there's your half. Oh, we didn't get close enough. That's your half. Here's your 75%. You're not going to see the other one. The other one's going to be too close. You have to Z-box even further. So your 0.25 is going to be, you see it. Of course you don't. It's wedged between this one and the x-axis, which you can't see. So you have to Z-box it on that to see it. So the point is that they're all collapsing down on 0. It's just the 0.25 is getting to the fastest, the 0.5 is getting to the next fastest, and the 0.75 is getting to the least fastest. Now, of course, this is all due to the fact that we have set those rates at 1/2, 3/4, and 1/4. We can mess with that too, can't we? If we set the rate at 0.9 or 0.1 or anything, I mean, this can be kind of fun actually. Make up a new rate of 0.9 to the x. Now predict where that one's going to be with respect to the other ones. Predict where 0.9 to the x is going to be with the other ones. And while you're at it, predict where 0.1 to the x is going to be with the other ones. Now I'm gonna readjust my window back to what it was before, so we see it, okay? So I'm gonna make my window 0 to 10 by 1s. We'll make y min 0, we'll y max 20 by 2s. Okay, so the first 3 curves you're gonna see are the same 3 we saw before. You ready? Here we go. There's your 0.5. Here's your 0.75. And then here comes 0.25, I'm gonna pause it.
Sean, what'd you make your y's?
I made y 0 to 20 by 2s. And the only reason I did that was I knew they were going to cross up here at 20, and I figured they're not going to get below 0. Okay, so you guys ready? There's 0.75 to the x. There's 0.5. There's 0.25. Where's 0.9 going to be?
Up higher.
Rob has a vote for up higher? Yeah? Up higher? How about 0.1? Going to be tucked in here, huh? Okay, here comes 0.9. Hot damn, there it is. Looking almost what, by the way? Looking almost, be brave. Looking almost linear. Because the closer that point whatever gets to 1, the more it's going to look like a horizontal line, a perfectly straight line. Nice. Ready for 0.1? It might go by kind of quick. There it was. But every single one of those curves goes through that point. Isn't that cool? Every single one starts at 20. And then drops at a different rate off to infinity. And they just get there more quickly or more. So essentially, think of it as different drugs with different half-lives. Take 20 milligrams of a drug with a half-life of 3/4 of a day versus a half of a day versus a quarter of a day versus a tenth of a day versus 90% of a day. The amount remaining in your body is going to be greater with a slower release rate, which makes perfect sense. That's what it looks like graphically, though. Is that fair? Yeah? Decent? Now these are all examples of exponential decay, which means as time goes on we lose. You can also have exponential growth. Let's take 5, because it's now 5 after 11, speaking of 5. Let's take 5 and look at an example of how exponential growth can also occur. Because that is a good thing. And I've got a fun quiz planned for you guys around exponential growth and finances. And also caution about that with student loans. So we'll come back to that as well. Oh, that's gorgeous. That's just beautiful. That's just beautiful. It's colors. Trust me. Hi. Can somebody, if you don't mind, Dina, can you turn the camera off? Just push that button on. I think it's, yeah, right there.